Good morning, everyone. The upcoming section is titled Efficiently Memory Profiling Distributed PySpark Code by Senior Backend Software Engineer Kaashif. And if you have any questions for a Q&A session, please use Slido to submit them. Now, let's welcome Kaashif from Bloomberg.
Hello, everyone. I'm Kaashif, and I'm a senior software engineer at Bloomberg. And as was just said, I'm here to talk about effectively memory profiling distributed PySpark code. So here's what I'm going to talk about. So the story I'm going to tell is mainly about you have some pandas code, and you're trying to scale it up. And there are various reasons why that can't work. In general. So I'm going to go through some examples and you'll see what I mean by that. One of the strategies you can use to try to scale up your pandas code is to convert your code to PySpark. And there are lots of do's and don'ts, caveats and pitfalls you can fall into when you're doing that. So I'm going to point out some of those and we'll look at some examples. And the third bullet point here is really where the meat of the talk is. Which is how do you diagnose and fix memory issues when you're dealing with distributed data processing with PySpark. The reason that's challenging is because the code executes across multiple machines, across Python and JVM processes, since PySpark is a binding of Spark, which is a JVM-based library. And the last thing I'm going to talk about is one of the more challenging cases, which is when you have business logic that lives in a native library written in C, C++, or Rust, and you want to use that with your Apache Spark executors, but you're running into all of these issues with scaling, like memory issues, out-of-memory issues, or just general slowness. So I'm going to go over that case too. So let's get into it. So the problem I'm going to use to frame this talk is a relatively common case, I think. So you have some Parquet files stored in S3. Parquet is a columnar data format that's commonly used in data processing. The example I'm going to go through is computing a weighted average. So this kind of thing is very common in finance. If you have, for example, the return on some securities and you want to average that in some way or aggregate that to a higher level, that kind of thing is pretty common. And the aggregation logic comes from a native library. So we're going to have a shared object that has native code, and we're going to be using that as the primary source for our business logic. The constraint here is each node only has 1 GB of memory. So in real life, when we're running these workloads, we run them with hundreds of gigabytes of memory. But I wanted something that you can run on your laptop and that I could run on my laptop to produce the examples for this talk. So the examples are scaled down, so the numbers are a bit smaller than in the real world. Okay, so what does our data look like? So here is one of the example Parquet files. It has 2 rows. And we have some weights. So on the left are the weights, the first column, and some values. And the algorithm in this case is super simple. It's just a normal weighted average. So you multiply each value by each weight, sum that up, and then divide by the total weight. So it's a super simple weighted average. Like I said, in real-world applications, when you have more complicated weighting schemes or more complicated types of averages or returns linking for securities that you want to do, it can be much more complex than this, which is why you might already have some complicated business logic library. In this case, super simple. We'll just go with this example, since it demonstrates all of the points I want to talk about. So just for completeness, I'm going to show you what it looks like when you're calling a shared object like this. It's not super important we're not going to dive into the details. This isn't a talk about, how do you call C code or Rust code in Python. But just to show you what the module we're using, since this is pretty central to the whole talk, So we have this shared object. We're using C types to define a Python interface to that. And the Python function we're actually going to call, so this weighted average function, exposes a NumPy array interface to that C function, and the C function just takes normal arrays. So in C, that'll look like a pointer and a size, and the output goes into another array. So these are both marked with the flag C contiguous because the function is expecting a row major layout for those arrays. You could also have F contiguous or something like that, which is like Fortran layout, but in this case, I guess it's a bit of a detail, but the flag is C contiguous here. So this is the function we're going to be calling to do our weighted averages. So the Python module doesn't contain the actual business logic, it's in the shared object. So that's the first point I want to make. So super simple example here. We have our Parquet file on disk, it's the one from before, and we're going to read that Parquet file and we're going to call our finance function to take a weighted average of that, the values in that Parquet file. So what it looks like here is you have this data frame, you convert it to a NumPy array, and you call the finance.weightedAverage function, and you print out the value. So what does that look like? You run it, it prints the value, so the weighted average is the first number there, and the sum of the weights is the second number. So super simple, works as you'd expect. Now here is the problem that we're going to be trying to solve. So you have a directory of Parquet files, much larger than your available memory. So in this case, larger than 1 gigabyte. That's not that impressive, I guess, but in the real world scenarios, you can have hundreds of terabytes or petabytes of data, and this starts to matter a bit more. So what you can do is you can try to read that Parquet file and do exactly the same thing as before, and let's see what happens. So you try to run it, and the Linux kernel out of memory killer kills the process. Because it's much larger than your memory, of course this can't work, right? So although it's obvious why this doesn't work conceptually, I think when we're starting with this example, it's useful to see what exactly is causing that out-of-memory error. So Memray is a great tool for this. It's a Python memory profiler, i.e. it shows you the memory usage of your program at the point where it's using the most memory. It was published as an open source project by Bloomberg a couple of years ago, and it can profile native code, i.e. when you're looking at your memory usage, and if it comes from C, C++, or Rust, or something else, you can see the native stack frames, and you can see the allocations coming from each C++ or Rust file. So I think that's, for us anyway, that's the killer feature of Memray, and that's why we use it. So to invoke it, it's super simple. You do Memray run with your script, and you can get a readable and interactive HTML report with some statistics. But the most important part is the visibility into the stack frames of where the memory usage is coming from. So let's try it out. Let's do it. So here's what we're doing. So we have our example from before. We run that under Memray. And of course, it still goes out of memory. That's what we expect. But what we get in addition is we get this file, this Memray example2.py.bin. That number there is the process ID, which is a bit of a detail, I guess. And then we can generate this HTML report using Memray flame graph, which will give you a flame graph of the memory usage at the time when the memory usage was at its peak. Which is just before it goes out of memory. And let's take a look at it. And this is going to look a bit scary, maybe, but the point here, so before you get intimidated by this, the point here is that you can see into all of the C++ stack frames. So what you're seeing here is a bunch of calls into the arrow library, which is what we're using to load the Parquet file. And you can see that there are a lot of calls here to do with reading the Parquet file which comes from the pandas read parquet function. So what's going on here is that, and I think this was obvious conceptually, but now we can see it in a nice visual format, is that when you load the parquet file, the file reader itself is what is using up all of the memory and causing us to go out of memory. So there's no easy way to load all the files all at once and get around this. So what do we do? So yeah, here's the conclusion. So it comes from reading the parquet. There's not really any way to get around this. If you want to load your data frame all at once onto one machine, you're just not going to be able to do that if you have data that's larger than the machine's memory. One way to solve it is to load the files one by one and do the processing file by file. That's not always possible depending on how much time you have available to run the computation. Because if you have 1 million files, you want to ideally parallelize that and not run that file by file. So here's what that looks like in pandas. When you're loading all of the data all at once, just to emphasize this, all of the data is loaded into one machine. You see all of these parquet files loaded into the one process on one machine. And if you have a multi-terabyte data set, that is eventually going to not work. So I guess I've seen a machine with 1 terabyte of RAM. I guess that exists, but when you have 10 terabytes or 100 terabytes or petabytes or exabytes or whatever, it will eventually not work. And you will need to use multiple machines. So the solution we're going with, there are other frameworks you can use, but what we use at Bloomberg is Apache Spark. So it's a framework for distributed data processing, which allows you to do 2 things. One, you can distribute your data set across multiple nodes. So that allows us to load the whole data set into memory at the same time. And 2, you can parallelize your computations across multiple nodes. And what PySpark is Python bindings for Spark, because Spark is a JVM-based library. Spark is written in Scala, and you can obviously call it from Java too, but PySpark allows you to call it from Python. So just to emphasize that, before we had all of the data on one machine in one process, and now you can scale horizontally with PySpark and load all of your data at the same time into multiple machines and multiple processes. So this is what allows you to load the whole data set at once. So here is what we're going to do, what we're going to try first. So if you want to move to PySpark and you have pandas code, one thing you can try is to switch your code to use PySpark.pandas. This used to be called koalas and is effectively a drop-in API-compatible replacement for pandas that you can use in your pandas code and will magically make your code scalable in various ways, and you'll be able to scale up, and there'll be all unicorns and rainbows, and everything will work fine. Great, so let's try it. Oh, it didn't work. So we have to use a different submitter script because we have a distributed, we have to submit to a Spark cluster. But what happens is quite weird. So if you haven't written PySpark code before, this error may seem a bit weird. But let's break it down. So the first thing you'll notice is that the exception comes from Py4j, which is the library that PySpark uses to bind Python calls to Java. And this comes from the collect to Python function. And the error we get here, you can see it's a really Java-looking exception. But the error is that the size of the serialized results of 6 tasks. So we ended up having 6 workers in our Spark cluster. And the size of the data set that we're trying to load is bigger than Spark driver max result size. So the problem here comes from the fact that df.tonumpy loads all of the data into the driver process. So we distributed the computation, sure, but at the end of the day, when we're trying to call our native business logic library, we ended up loading all of the data into this gigantic NumPy array, and Spark blocks that by default. So this config value here, Spark driver max result size, is something you can change, and it's just a preset limit that Spark has to prevent you from loading gigantic data sets and serializing that, because it can be really slow and is a sign that you wrote your code incorrectly. So let's try to see what happens if we increase that value. So when you're submitting your Spark job, you can change that value, but it still doesn't work. So this error here is even more perplexing, perhaps, than the last error, and it comes from, again, from Java. But if you Google this error or you follow this link, which you can't follow because you're looking at this, and I don't have the slides online yet, but if you followed this link, you'll see that this error comes from the Java process going out of memory. So collect to Python still errors out. This is still coming from collect to Python. And the error comes from out of memory in the driver. So the problem here is still the same. We're loading all of the data into the driver process, and that causes us to go out of memory, which makes sense. We still have a more than 1 gigabyte data set, and you are never going to be able to conceptually load that all at once into a machine with only 1 gigabyte of memory. So this is one of the points I want to highlight. When you're trying to scale your code up, your pandas code, and you're trying to use PySpark pandas, so the pandas on Spark API, if you do this naively and don't really understand what you're doing, you may run into all these kinds of issues. So the first one we saw is to NumPy. That's an obvious one because it loads all of the data into the driver, into one process. But there are other gotchas too. So there are other kind of foot guns where in pandas the function is super fast and super cheap, but in PySpark they are expensive for various reasons which we'll get into. So there's dataframe.shape and there's apply, and these have, in some cases, a bit more subtle gotchas that you have to be aware of. So this is the one we just saw. This is just a summary of what we saw effectively. So when you see these kinds of errors coming from collect to Python, that is a sign that you're collecting your data set into one node, and you just shouldn't do that. The whole point of Spark is to run distributed computations, and in some cases, you'll have to really think about how you can distribute your computation. If you just have, if you have pandas code that runs all on one machine, you are probably going to have to do some work, and maybe not rewrite the code entirely, but do some thinking about how to distribute that. So in this case, it was super obvious. This example is constructed to do the wrong thing and load the data set into the driver. But this is not how you're supposed to use Spark, and we'll see how to correctly use Spark later on. So here's another example. This is a bit more subtle. This is calling dataframe.shape, which gives you the dimensions of the data frame. And the funny thing is, PySpark.pandas, the data frame shape function there is super slow. And what happens when you run shape in PySpark is that there's this gigantic fixed overhead from submitting the job to all of the workers, running the Java processes, spawning the Python workers and all of that. But even when you take that away, it's still, in some cases, much slower. And pandas data frame shape is close to free in some cases. I should have written in some cases there, but if you, for example, do this, so you have, you load a Parquet file and you look at the index is a range index. This has 100 million rows in this data frame. And if you take the length of the data frame, it runs almost instantly. And if you look at the pandas source code, when you have a range index, it's really just doing arithmetic. So you have start, stop, and step, and you can do some arithmetic. It'll be a couple of instructions on your CPU, and it will be super fast. It will not do any I/O. It will not do anything scary. It will be very fast. But when you have a PySpark data frame, it's much more expensive in some cases. So calling a Spark data frame count can be super expensive for various reasons. So in the worst case, it can require a scan of the entire data frame. If you did something like filter the rows of the data frame, that will happen lazily, and when you run count, you just don't know without actually scanning the whole data frame and running that filter function how many rows there actually are in your data frame. So at the point when you run df.shape, that may actually take a significant amount of time because there may be an unknowable number of operations that have been lazily stacked up there or something like that. So don't assume df.shape is free. One funny case where this materializes sometimes is when someone just logs the shape of the data frame. They're like, why did logging the shape of this data frame take 1 hour? Like, I don't understand. The reason is they may have converted this code and not understood that shape actually has these Spark operations underlying that may be lazy. So be careful of that. And the last case I want to highlight here is data frame apply. So this is a case where it's not just slower in PySpark pandas, it's actually different. Your code will behave differently if you just do this naive find and replace type migration. So in pandas, if you use axis equals 0, f is going to be called with the whole column, and you'll get that whole column as a series. And you can do things like, sum the whole column or take the average of the whole column, and that will work fine. In PySpark, f is called once per batch of rows, and you may wonder, what is a batch? And the answer is that there are really no guarantees about how many rows there are in each batch of rows. All you know is that each batch, when you union those batches up, you'll get the whole data frame, but you don't know anything about how many batches there are. So if you're trying to do something like a global aggregation, like take the average of the whole column, you can't do that in this way. You have to do something else. So that find and replace, the happy path is really where you notice that you did something wrong, but the unhappy path is where you have code like this. So this is pandas code, which works perfectly well. You're just summing up the whole column, and it works fine. And if you convert this to PySpark.pandas, you will notice that something weird happens. You get these multiple sums. Even though previously in pandas you got one sum for the whole column, now you get one sum per, and you're not sure what it's per exactly because the row batches can be any size. So you can see here that they're all the same size, and it's just the numbers are increasing because the range is in order and the row batches happen to be divided up like that, but you really don't know. And the danger here is if you don't notice that you did something wrong. So when you naively translate your pandas code for your small data sets, so if you have a test with 5 rows in it, for example, this will work the same. You'll get your one sum or your one average or whatever, and you won't notice. So in your tests, your test may pass, and you'll be like, yes, my find and replace migration from pandas to PySpark worked correctly. But that is not the case. So when you scale that up, you'll get something weird going on, as you saw on the previous slide. So so all of this so far I haven't linked to the documentation, but if you read the documentation, it is super obvious, and there is a gigantic warning. It is in blue, but I think it should be in red on this page about the difference in behavior when you're going from pandas to PySpark pandas. So be careful of that. This function behaves differently. Okay, so to conclude this section, our dependency, which is the native library, exposes a kind of NumPy or array interface, so we do have to eventually convert to that. We can't avoid that. But the strategy, and you do have to think about what your business logic looks like to properly distribute your code. So our strategy in this case is to aggregate each partition and then aggregate the results. So you can take a weighted average of each partition, so each file, and then you take the average of the results, and that will work fine. And the function we're going to use for that is this map-in-pandas function, which is not a PySpark pandas function. It is just from PySpark. And it's not a emulation or API-compatible drop-in for anything from pandas. The one thing, so I do want to highlight as well that in this case, if you do this two-stage aggregation process, you're doing your additions and multiplications in a different order, so you're going to get different answers. This isn't a talk about floating point multiplication or addition, but it's not commutative or associative. And if you change, so commutative means you can change the order and you get the same result, and associative means you can change how the operations are bracketed and you get the same result. So floating point addition and multiplication don't have any of those properties, and you'll get different numbers, and it won't be deterministic either. So be aware of that. This doesn't come for free. So I mentioned map-in-pandas. What map-in-pandas does is it takes an iterator of data frames. So you give it a function that takes an iterator of data frames and gives an iterator of data frames, and PySpark will take care of distributing the data and work across nodes. So this iterator of data frames that your function gets may not be the whole data frame. There are going to be multiple invocations of this function across multiple nodes and multiple Python workers. So that's why this is distributed, and what we were doing before, i.e. converting to NumPy in the driver, is not distributed. So these will run in the workers, and you can scale them horizontally. So what does our more scalable code look like? And most of it is similar. So in this case, we're using PySpark SQL to create our Spark session. So we're not using or relying on the supposedly drop-in PySpark pandas API. So our first function here is what we're giving to map-in-pandas. That takes an iterable of data frames. And for each of those data frames, we take the weighted average. And we return an iterable of data frames, each with one row, with the average of each chunk that we got. And then we have this so we have this data frame here that represents one row for each chunk, and that row contains the total weight and the average value. And then the last thing we do is we do have to convert to NumPy and take the weighted average of that in the driver, but by this point we have only one row per partition, and this will fit in the driver fine. So let's run it and see what happens. I'm so excited. Does anyone think this is going to work? There's time left in the talk, so it's not going to work. Oh, spoiler alert. It doesn't work. It still goes out of memory. So we ran our function on small chunks. It still didn't work. I mean, what's going on here? So let's take a look. So if we're running code in executors, it's kind of non-obvious how you profile that, because if you profile the driver using Memray, you'll only profile the driver code, and there are other Python processes, and there are there's other Python code running out there that's not in the driver. So that won't work naively. Spark 3.5 has built-in memory profilers using the memory profiler package, and you can profile, Python, Java, Scala, whatever, using various built-in Spark features. So cprofile, in this case, we don't care about runtime really. We just care about memory. cprofile, you can do something funny that I've seen before, which is where you provide a timing function that measures memory usage. That's kind of an abuse, and it's kind of funny. I've seen it in a talk before, but that's not what we're going to do here. And of course, Memray is what this talk is about. And spoiler alert, I'm going to go with Memray, but let's pretend to consider the first options. So PySpark has a built-in memory profiler. Like I said, you set this config value to true, Python profile memory, and at some point you call the Spark context show profiles to show the memory usage of your code by function or by line. So let's try to run it. And I mean, there's still time left in the talk. Do you think this is going to solve all of our problems? I don't know. Oh, it didn't work. Wow. So yeah, it turns out that the Spark memory profiler doesn't support profiling UDFs. So UDF stands for user-defined function. It doesn't support profiling UDFs with input and output being iterators. And map-in pandas uses a UDF, and we have iterators of data frames as input and output. So that's not supported. That's unfortunate. So we can still use Memray. We just have to do something a bit different. So inside the function that we're passing to map-in pandas, you can add this code to profile the code that you're running in executors. So this with block here has this memray.tracker context manager that we're using. You pass it the file name to output the profile to, and you pass it this native traces equals true keyword argument, and that will enable native traces, i.e. Stack frames from inside our shared object to show up in the profile. So you add this in and you run it, and this is what you get out. So the green stack frames here are Python stack frames. So you get the print weighted average. You notice there are also C stack frames here, so you may recognize PyObject make TP call as a something from CPython. So that doesn't come from the code we wrote, that comes from something in between our Python code and our native library. So there are there's obviously some cases where you can't print the name of the function or the file. The reason for that is I didn't build the Python interpreter with debug symbols, which maybe I should have done. But our shared object that we wrote does have debug symbols. So you can see that there's this weighted average at source/lib.rs, line 6. So this library is written in Rust, it turns out, and you can see into it to determine where this memory usage is coming from. So there's some rather suspicious vector reserve calls here. So there's this vector is a data structure in Rust that you can reserve memory for, and you'll notice that basically 100% of the memory usage is coming from that reserve call, and you can see that we're calling a bunch of allocation-related functions under that stack frame. So let's look at source/lib.rs line 6, and let's see what's there. So I made it super obvious for this because I didn't want to do like a Rust profiling deep dive or anything. In the code that we wrote, there's a scratch.reserve 100, I don't know how many zeros are there, a billion? Yeah, reserve a billion F64's worth of scratch space for some reason. Obviously this is artificially constructed, and I put this here to intentionally trigger the out of memory. But the point is that Memray allowed us to track down this allocation exactly and go to the exact line where the allocation is coming from, regardless of the language your native library is actually written in. So please ignore all of the other Rust code on this slide. I know this is a Python conference, but if this, there's a lot of details here that are frankly irrelevant. So the important part here is that this reserve is where the memory usage is coming from. So let's get rid of it. So I literally just deleted this line and recompiled the shared object. And it works. Great. So you'll notice these numbers are exactly the same as the numbers on the first slide. The reason is I just copied the same Parquet file over and over again and deleted, jiggled the weights a bit until it gave exactly the same numbers. The funny thing is here, I guess maybe this whole thing was a waste of time because you get the same numbers, but I think we learned something along the way about how to scale this code, and it was pretty useful. So let's sum up. What did we learn from this? So the lesson I want to the lesson I want you to take away from this is that when you're converting your pandas code to PySpark for scaling reasons, you should be careful. If someone is telling you that pandas on Spark is super easy, totally API compatible, that is mostly true. So it's very convenient to do this find and replace, but you have to go through and understand what your code is doing. So naive usage, i.e. those functions I mentioned before, like to numpy, shape, apply, and there are many others too, like transform. They're doing things that you may not necessarily be aware of, and those things are different when you have pandas and PySpark code. So be careful about that. One tool that we have found invaluable is Memray. So it's not just for PySpark or pandas. You can use it for any Python code, any code that uses C, C++, Rust, or any other native extension that produces a shared object. It's great for digging into these issues, and it has lots of great features that you can't find elsewhere in other memory profilers. So again, I don't think I can stress this enough. If you have these kinds of issues, rather than guessing and trying to come up with a solution, your conceptually obvious solution may actually be wrong, and you should profile instead of trying to guess. So profile, 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 those are the 3 lessons I want you to take away from this. And I hope you go away and try this out. So if you want to learn more about how we use Python at Bloomberg, take a look at this link, tech@bloomberg.com/Python. And if you want to do what I just recommended, which is try out Memray, it's fully open source. Go to github.com/Bloomberg/Memray, and you can see that, and you can install that straight from PyPI. So please do go away and try that. And I think that's it.
Okay. Thank you, Kaashif, for your excellent presentation and sharing. And now here we have a Q&A section. Okay. The first question is: have you considered or tried other libs like Polars or Dask?
Yes. Now the reason, so Polars and Dask are great solutions. Polars is not API compatible, and it's not even supposed to be API compatible with pandas, which some think is a good thing. It's written in Rust, and it provides this Python interface, and it's really high performance. We do use it sometimes when doing data analysis, but it's not really a distributed processing library. Now, Dask is a library that does distributed processing. We don't use it just because we have these gigantic Spark clusters that already exist, and everyone is using Spark at Bloomberg, including people who write Java, Scala, and other languages. So we really just went with what we already have, but Dask is a good solution if you want to scale as well. We just happen not to use it.
Okay, the second question is: I really enjoyed the talk. Will you publish the slides somewhere later?
Yes, so I'll try to send out the link to the slides later. There was some kind of intellectual property approval I had to go through to do that, and I didn't get it done in time for this. But I will try to get that done and publish the examples too in a runnable form so you can just run them. But yes, I do recognize that I should have done that before this. I was too slow. My apologies.
Okay, the next question is it easier to do the migration with Python UDF in PySpark?
So Python UDFs are, so like I said, the map in pandas function that I went through does use UDFs internally, and that's great. UDFs do work great. I will say that probably if you're rewriting your code, the ideal thing to do would be to try to use built-in Spark operators. So when you use a Python UDF, you have to, and there's no way to get around it, serialize your entire data set and send that from JVM processes into Python processes. So that is going to be slow and it's going to take a lot of time. It doesn't matter how efficient you get it. You can turn on Arrow as the serialization. You still have to do this I/O. And I would suggest using Spark operators, native operators, instead of Python UDFs. Python UDFs could be easier, and that's probably, that's a good option if you want to translate your code and keep it the same, but it's going to be slow. So try to use built-in Spark operators where possible would be my recommendation.
Okay. The next question is, do you consider checking large data sets and using Python multiprocessing to async to use pandas to process data?
Yes, so that's one way to do it. But what you'd be doing there effectively is rebuilding what Spark does yourself. So if you want to have multiple processors and you want to have multiple machines, you would have to build up this whole thing to distribute that work across multiple machines. And if you just use multiprocessing and just use async IO and pandas, it does get you the multiple processes, but at the end of the day, if you're just using pandas, you could have one big process and have it fill up the whole memory on that one machine. So you would need to go further than just using multiprocessing. You would need to have that across multiple machines. So we did consider something like that, but ultimately, PySpark already exists and is mostly, I guess, other than the caveats that I mentioned, easy to use. So that's why we went with PySpark.
Okay, the next question is, the key is how to make the data distributed in Spark. If data that wasn't easy to distribute initially but found a solution, could you share with us?
So that's an interesting question. I think it's asking for an example of data that wasn't easy to distribute initially. In this case, the data was super easy to distribute initially, so it may not be a good example for this. We do have some examples of this kind of thing, and I think we should talk after to make sure I understand the question exactly. I don't know who asked it, but yeah, this example is like super contrived and constructed to not expose anything, any internal data from Bloomberg or proprietary information, which is why it's so simple. So we should talk after, and I could share something about that.
The next question is, do Memray require debug built for the native library so it can keep track of the symbols invoked by your code?
So this is a good question. So the top level symbols invoked by your code already need to be visible for the shared object, for calling your function in the shared object by name to even work in the first place. So if we didn't have debug symbols in our shared object, you would have still been able to see the weighted average function using all of the memory, but you wouldn't have been able to see which line it came from or any of the lower down details like the vector allocate, for example. So to see anything further down, any stack frames further down past the top level and not have it show up as unknown, unknown, at unknown, or whatever, you do need debug symbols in your library. And at Bloomberg, we generally have debug symbols for everything. So it does work for us, but you would maybe have to rebuild your library.
Okay, the final question is, can Memray be used for production monitoring? If can be reported to Grafana?
So what Memray produces, so you can use Memray for production monitoring, but it doesn't work in quite the metrics type way that I guess is being implied here. So if you want to use Memray for production monitoring, what you can do is you can turn it on and you can look at there are a couple of cases. You can look at the live memory usage of your program. So if you have a process running, it's using a lot of memory, you can run Memray and get a snapshot of the memory usage broken down by which function is calling what. Or you can turn on, like we have here, a dump of the memory usage if the program crashes. So that is a kind of production monitoring too. But Memray doesn't support, as far as I'm aware, live reporting of memory usage metrics or anything like that. So you wouldn't really have anything to put in Grafana.
Okay, that is the end of the program. And thank you, Ms. Kaashif, for an excellent, wonderful presentation. And let's give our speaker a big round of applause.